This video is all about mathematical modelling with quadratics. We're going to start off by looking about what mathematical modelling is, and then we will apply it to quadratics shortly with an example. So mathematical modelling is a process that you're going to be using throughout the rest of your A-level, both in terms of pure and applied maths, and hopefully continuing to do so at university and onwards in your career, because it's a really powerful thing. It is basically the process of taking a real-life situation and coming up with an equation for that real-life situation so that you can examine what would happen in certain situations. We do so by making assumptions to simplify the problem so that we can decide whether what sort of model would be suitable for it. Would a linear equation be suitable for it, or a quadratic equation? Or perhaps we'll see later this year a trigonometric equation might be useful, or an exponential equation, or if we're interested in how things change, then a differential equation. We'll see how we could use those in year 13 to model these real life situations. So once we've decided what type of model to use and we've come up with an equation for it, we can then start to put numbers into that equation and see how realistic our answer is. Does it match up with what's actually happening in real life? If it does, great. If it doesn't, then that's fine. We can then try and refine and improve our model. We can adjust it slightly by adding other factors into it, by taking things into account, by coming up with ways to model the assumptions that simplified the problems previously. By adding those things into the equation, then hopefully we can get closer to actually what's happening in real life, and then we can start to investigate more accurately. So that's the idea of mathematical modelling. Let's have a look now at how we could use a quadratic equation to do so. So let's just remind ourselves what we know about quadratics so far, because we've been studying them quite a while. We know that we can write them in this usual form, ax squared plus bx plus c, where if the a at the front here, if that's positive, then we know the quadratic is going to look like this. If with a minimum point. If that a is negative, then it's going to look like this with a maximum point. This way of writing is particularly useful for finding the roots. So that's finding the x coordinates when y is equal to 0. We know that we can also write it in completed the square form, which is particularly useful for finding out the coordinates of the minimum point here or the maximum point. So we know quadratics will look like either a parabola like this or a parabola like that. That's the posh mathematical name for quadratic. Now you'll have probably noticed that the first slide I had on this video, these are all parabolas. These are all real life situations that we could come up with a mathematical equation to see what's going to happen. If I was interested in how far this footballer was kicking the ball, or how high he was kicking it, or if he changed the angle, what effects would that have on how high or how far he could kick it? I could investigate all of those things with a quadratic equation. Similarly, if I was interested in how far this baseball player could throw the ball, I could look at that with a quadratic equation. If I was interested in whether I should fire a cannon at this angle or should I fire the cannon at this angle, we could start to investigate that with quadratic equations as well. Or if you're interested in engineering or architecture and we wanted to examine this building here, we could do that with a quadratic equation possibly. Or maybe you're an economist and you're looking at the share price and you're wanting to find when's the best time to buy or sell a share to maximise your profit or minimise your loss. You could examine a share price with a quadratic to find the best price to buy or the best price to sell. So now that we've talked about mathematical modelling and we've talked about quadratics, let's have a look at an example where we can put those things together. So, a javelin is thrown over level ground from the top of a tower. The height in meters above ground after t seconds is given by h of t is equal to 12.25 plus 14.7t minus 4.9t squared, where t is greater than or equal to 0. So let me just draw what's happening here. So you can picture the parabola, you can picture the quadratic. Here's the tower, here's my athlete throwing a javelin, and the javelin is going to travel like this, in the shape of a parabola. And what this equation here is telling me is that I can work out the height above the ground at any time by substituting t into this equation. If I wanted to know how far above the ground it is after 1 second, all I would need to do is substitute 1 here and here. You can see we have a negative 4.9 squared because my parabola is a negative N shape. So now that hopefully that equation makes a bit of sense for this situation, and hopefully you're picturing what's happening here, let's have a look at the question it's actually asking us. It's a multi-part question. Part A says, interpret the meaning of the constant term. This is the constant term here, and that happens when t is equal to 0, and I'll show you why. If I substitute 0 into this equation, I get 12.25 plus 14.7 times 0 minus 4.9 times 0 squared, and obviously 14.7 times 0 is 0, 4.9 times 0 squared is going to be 0. So the constant term at the front there, the 12.25, that is the constant term, and that is the height when t is 0. The constant is always going to be the value when the time, or the variable more generally, is equal to 0. And therefore that is the initial height. Initial because time is 0 and height. So it is the initial height of the javelin above the ground. So the initial height from which the javelin was thrown. Right, part B. How long does it take for the javelin to hit the ground? Well, hit the ground, that's making me think that the height above the ground must be 0. If it's in the ground, if it collides and it's stuck in the ground, then its height above the ground is 0. So I'm going to make the height, my equation, equal to 0. So 12.25 plus 14.7t minus 4.9t squared equals 0. So we can solve that then. This is my A value. So that's my A. This is my B. And this is my C. So using the quadratic formula here, or you can use the quadratic solver on your calculator, I find that t either equals 3.68 seconds or t equals minus 0.68. Now obviously the negative time here I am not going to use. This is the answer I'm going to give. So I'm saying that the javelin is going to hit the ground after 3.68 seconds. Part C. After how many seconds is the javelin 17 metres above the ground? So the height is now 17. So if I now take my height equation and make that equal to 17 this time. So in order to solve this, I'm going to rearrange to make it equal to 0. So I'm going to subtract 17 from both sides. So 12.25 take away 17 is minus 4.75. And again, we have now got an equation to solve where we can work out what the value of t is. So solving that, we find that t is going to equal 2.63 seconds, or t would be 0.37 seconds. So we've got two values for the time there actually, which should hopefully make sense. Let's just remind ourselves what we've just done there. We're saying our athlete was here, throwing the javelin from the top of the tower. This initial height here was 12.25. The javelin's going like this, it hits the ground, so the height is 0 over here. It hits the ground after 3.68 seconds. And we are saying that it is 17 metres above the ground in two places. 17 metres above the ground here at the 0.37 seconds. And it's also going to be 17 metres above the ground here at 2.63 seconds. So getting two answers for that should actually make sense, because the javelin is going to pass through 17 metres above the ground on its way up and on its way down. Next, we have been asked to write h of t in this form. So basically it's asking us to complete the square on this. So first thing I'm going to do is rewrite it in its usual form with the a at the front. Next, in order for me to complete the square on this, I have to factorise the minus 4.9 out. I have to have just a single t at the front, a single t squared at the front there. I'm now going to do the 14.7 divided by the minus 4.9, which gives minus 3t. So all I've done there, I can't have this minus 4.9 at the front, so I factorise that out. And whilst factorising that out, I've divided the 14.7 by the minus 4.9 to give minus 3 there. But now I can actually complete the square. So let's leave that there for now. Let's complete the square on what's inside those square brackets. So this t squared minus 3t will become t minus 3 over 2, all squared, minus 9 over 4. Now we're going to multiply through by the minus 4.9, so minus 4.9 times this, and minus 4.9 times the minus 9 over 4 will give minus 4.9 t minus 3 over 2 squared, plus, because we've got the minus 4.9 times minus 9 over 4, so plus 11.025. Not forgetting the 12.25 from the end there. So all I've done there, this times this is this times this is this, plus that bit on the end. All I'm going to do now is just simplify this a little bit. So I'll say h of t, my two constant terms, add those together to be 23.275 minus my 4.9 t minus 3 over 2 squared. That is my answer to part D. Part E. Hence, so using what we just did, write down the maximum height the javelin reaches. Well, I know that this is going to be the maximum height. Remember, completing the square always allows you to just read off what the maximum or minimum is going to be. So max height is going to be 23.275 meters when, because I need to say when this occurs, well, that's going to be when t is 1.5 seconds. And there's one final part to this question. It asks me to comment on the validity of the model for large values of t. So is this a sensible model, specifically when t becomes big? Well, remember what we're saying here. We've got our athlete who's throwing the javelin and it lands on the floor after 3.68 seconds. Well, large values of t, what happens after 3.68 seconds? After 3.68 seconds, so when t is 4 or 5 or 6 or 7, or if t is greater than 3.68, there's a problem because the model is saying that it's going to be below ground. If you substitute any of those numbers in here, you're going to get a negative answer. If you substitute 4 into this equation, or 5 or 6, you will get a negative height, which suggests that the javelin is continuing to travel below the ground and not being stuck. So that's the issue. The model is not valid for t greater than 3.68 because it suggests negative heights, which is not possible in this case. And there we go. That is the idea of mathematical modelling applied to quadratic equations with an example.